In the last video, we looked at orbital diagrams and electron configurations as a really good way of mapping where the electrons can be found in an atom without having to draw these three-dimensional orbital things that are kind of crazy if you were to draw them all out on paper. And that when you saw these orbital diagrams, the boxes were labeled like 1s, 2s. And like when we got to the 2p orbitals, there were 3 boxes there for you. And so it was somewhat simple to just go through the boxes and fill them with arrows, right? I mean, we were thinking about filling low energy to high, and we were thinking about, you know, the equal energy p orbitals and d orbitals and filling them 1 electron at a time. But we didn't have to like draw out all the boxes, and I didn't have to remember like the order, like, so what orbitals come next? And honestly, I don't want to have to memorize that. You know, like, what if I had to do the electron configuration and they didn't give me all those boxes first? So now it was easy because once I had the boxes filled, and then I could go to the even shorter version, electron configuration, by just saying like 3d6. Well, yeah, I knew that because the boxes were there and I could just fill them in with arrows. What if I didn't have any of that? Do we have to memorize like the order that the orbitals fill? Because that would be a pain, right? Nah, you don't have to memorize any of that. The periodic table is full of magic, and it will tell you the order that the orbitals fill. People are always kind of like, you know, why is the periodic table the shape that it is? It's kind of a weird shape. Like, why isn't it just a box? Why do some groups have more elements and some have less? Well, a lot of it is based on the properties that we try to group elements together that have similar properties, but we also have grouped elements based on what orbitals they fill. And so you've got this group of 2 elements that kind of go across at the beginning here, like these guys. This is called the S block. These are elements that fill s orbitals at the end of their configuration. They'll end with something S1 or something S2. It's called the S block. It goes across 2 elements because the s orbitals can hold a maximum of 2 electrons. Over here, this is called the P block. It kind of starts with boron and goes across to neon and downward. Now, we'll talk about helium in a minute, but somebody might be saying, where's helium? I'll get there. But notice that this group on the periodic table goes across 1, 2, 3, 4, 5, 6 elements to represent the fact that you can have up to 6 electrons in the p orbitals. So you could have like 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Same thing with 3p, 4p, 5p, 6p, and up to 7p. Those would be some big dumbbell-shaped orbitals, right? There's a block in the middle. It's called the D block. The D block kind of starts with number 21, scandium, and goes across to zinc and down. That block in the middle goes across 10 elements to represent the fact that there are 5 d orbitals and they each hold 2 electrons. 5 times 2 is 10. No. Now, your periodic table might not look exactly like this, where there's an F block. And I think we kind of mentioned that there are up to 7 F orbitals, and each can hold 2 for a total of 14. Well, your periodic table might not look exactly like that. And in fact, I bet it looks a little bit more like this. So if you've got your book in front of you, flip to the very back cover and you will have this periodic table. And we're going to write on it. And you'll be able to use this periodic table on any test or quiz then. And it's going to have all kinds of good stuff marked on it. Okay, so this first two columns, or first 2 groups, on your periodic table, we're going to block this off like so. And then we're going to put a big S in there. That's the S block. Goes across 2 elements to represent the fact that there are 2 electrons that can fit in the s orbital. And there's only one s orbital. Fantastic. Now, when you get over to boron, we're going to go across from boron to neon and all the way down. Sorry, helium. We're going to leave him out for now. This is the p block. It really does go across 1, 2, 3, 4, 5, 6 elements. Magic. To represent the fact that you can have up to 6 electrons in the p orbitals. So these elements will all end with electrons in p orbitals. No way. In the middle, we're going to block off these guys. Like scandium over to zinc and all the way down. Yes, this is the D block. I'm write a D in there. The D block should go across 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, it does, 10. To represent the fact that there can be up to 10 electrons that fill the d orbitals. So all of these guys in the middle will have an electron configuration or orbital diagram that ends with electrons in d orbitals. Now here's the deal, and this is for real. Periodic tables should look like this, with this F block kind of like right after the S block. But the F block on most traditional periodic tables is actually pulled out to the bottom. This is the F block, for no better reason but to make it fit better on a standard sheet of paper. For real, that's it. Otherwise, the periodic table just gets really long and skinny. And to be honest with you, these F elements are often radioactive, they're synthetic or like man-made, they're highly unstable. They're really not elements that we'll ever experiment with in the lab. And so it's kind of okay. We'll pull those guys and leave them at the bottom. But it really does go across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It goes across 14 elements to represent the fact that there are 7 f orbitals and they can each hold 2 electrons. Cool. Okay, now here's the other thing that we're going to mark in. I'm going to switch to a different color. Yeah, my purple. Let's do that. Okay, so now on the side here, you'll notice that these are the rows going across are numbered. Like here, there's the number 1, 2, 3, 4, 5, 6, 7. The numbers going across are going to represent the energy levels. Ah, interesting. So now watch how magical this is. Although first I'm going to mention helium. Helium has a little bit of an identity crisis. We don't know where to put him. Helium's electron structure looks a lot more like beryllium, magnesium, and calcium. So I'm going to put like a little ghost helium in here. I'm going to put like a little helium. And for electron purposes, I'm going to pretend that helium really goes over here. His electron structure looks more like beryllium and magnesium. Well, he's in that last group because his properties match a little bit more closely with neon, argon, krypton, xenon. But it's like, where do we put him? I can see reason for helium being in either group. Yeah, he goes with his properties. But for electron purposes, we're going to put him on top of beryllium. Okay, now watch this. You don't have to memorize the order that the orbitals fill. You just start with hydrogen, and we're going to walk our finger through the elements, and it will tell us the order that the orbitals fill. And it'll even tell us how many electrons would be in that group of orbitals. So for example, hydrogen is the first element. It's in the first energy level, so this is like the energy level. It's in the first energy level. It's in the S block of the periodic table, and it's the first element. So hydrogen would fill the 1s orbital with 1 electron. Helium would be the second element. First row, first energy level, S block. We'd say its configuration is 1s2. Sweet. And then technically, if we're putting helium on top of beryllium, if I walk across, there would be no other elements in that first row. Yeah, because there's no other orbitals in the first energy level of the periodic table, or in an atom for that matter. So like there's no elements that would be 1p. Sweet. The only elements that just fill the 1s orbital are hydrogen and helium. Now when I get to lithium, I'm in the second energy level. I'm in the second row. Second energy level. Lithium and beryllium are in the s block. They fill the 2s orbital with 1 and 2 electrons. So their configuration would always start 1s2. I mean, almost everybody starts 1s2. But then lithium would be 1s2, 2, second energy level, or second row, s block. Lithium is the first element in, 2s1. Beryllium would end 2s2, second element in. And now I would highly suggest when you walk across the second row or the second energy level, now we're going to hit the p block. By boron, just put like a little 2 in there, because that will help you to remember that the first row of the p block is not the first energy level. It's actually the second energy level. So like when I get over to boron, it's going to be 1s2. You always start with the first 2 electrons. Then 2s2. Then I walk across to the p block. I'm still in the second energy level. P orbital, p block. Boron is the first element in. Oh, sweet. And you'll kind of see, like, they give you part of the configuration. Like, it shows this helium in brackets, and we'll deal with that eventually. But then you kind of see under the symbol B, it has 2s2, 2p1. That's giving you the configuration. Carbon would be the second element in the 2p orbital. So it would end 2p2. Oh, all we have to do is like just keep filling the orbital. We just keep walking our finger across the rows of the periodic table. Fluorine would end with some, I suppose you could put 1s in the front instead of helium, and we'll deal with that. 1s2, 2s2. Fluorine would be the fifth element in the 2p orbital. Second energy level, p block. And finally, when you get across to neon, you would have filled the second energy level. Second energy level only has the s orbital and the p orbitals. If you had 11 electrons, that 11th electron will go in the third energy level. So the third energy level would start with an s. Sodium and magnesium would fill the 3s with 1 and 2 electrons. Then we'd follow across. And by aluminum, I would write a 3 to remind you that this is the 3p. I get that it's the second row, but the p's don't start till the second energy level. And so same thing as the 2p's, now you're just in the 3p. Aluminum through argon will just keep putting one more electron in that 3p orbital. And now here's where that discrepancy comes up, where we would think that after the 3p we should go and fill the 3ds, but there's this weird, order of orbital fillings. It's not what I expect, where the 4s kind of sneaks in there because the 4s actually has less overall energy than those d orbitals. The periodic table will tell you. You don't have to memorize it. Just walk your finger through the periodic table. After I fill the 3p, like after argon, look at the next available orbital. I'm starting the 4th row. I'd be in the S block. Potassium and calcium will fill the 4s orbital with 1 and 2 electrons. But now here's how the periodic table will help you. When you get to the D's don't start till the 3rd energy level. So by scandium, write in a number 3. That'll help you remember that when I think about like labeling my periodic table, well, the S block starts with 1. So when I number the S block, S orbitals are in every energy level 1 through 7. Well, P's don't start till the 2nd energy level. So when I label my P block, I start with the 2nd energy level. D's don't start till the 3rd energy level. So when I start numbering my D block with a 3. But now this will help me to remember that when I hit the 1st row of the D block, it's actually the 3D. So scandium all the way across to zinc will fill the 3D orbitals. And now when they have these configurations in the boxes, like for example zinc, they have zinc with 3D10, and then they list it as 4s2. I don't do it that way. And actually, this would be a little more of a non-traditional way of showing it, because we want to show the order from low energy to high. I don't necessarily want to just see like all the orbitals organized by energy level, like 1st level, 2nd level, 3rd level. More traditionally, you'd see 4s2, 3d10. So this I'm going to give like a little face, the way that it's written on these periodic tables. More often, you'll see it like this. This is better. Because then it's showing me that the 4s actually fills before the 3d. And the periodic table tells me that. I just walk my finger through the elements, and as long as I can mark up my periodic table, it tells me the order the orbitals fill. Now watch this. When I get back to the P block by gallium, we're going to put in a 4. Now we go back to the 4P. And so to be honest with you, when I number my periodic table, when I label it for electron configurations, if I have a periodic table and it's not already numbered down the S block, I put the numbers 1 through 7. Now this one was already numbered, which is fine. I always start 1 through 7 as I go down the S block. There's always an S orbital every energy level. When I hit the P block, I number it starting with 2. And then I just go right away and put all the numbers in. 2, 3, 4, 5, 6, 7. The P's don't start till the 2nd level. The D's don't start till the 3rd, but then I just number them all. 3, 4, 5, 6. Guess how I'm going to number that F block? The F's don't start till the 4th level. So by lanthanum, I'm going to put 4F, and by actinum, 5F. And to be honest with you, we're not really going to do configurations with F orbitals because they're not elements that we're going to ever study anyways. But if you were curious, it'd be the 4F and the 5F. When I do a configuration, the very first thing I do is label my periodic table. I block off the S block, P block, D block, maybe the F's. And then I number them. S's start 1 through 7. P's are 2 through 7. D's are 3 through 6, but maybe if new elements are discovered, there'll be a 7D someday. And then I just walk my finger through the rows of the periodic table, and it tells me the order. So after, like in this 4th row, I go 4s2, 3d10, then I'm in the 4p for 6 again. So gallium through krypton will fill the 4p orbital with 1 to 6 electrons. And then you just keep walking your finger through the rows. Next I'd be in the 5s. I go 5s2, 4d10, 5p6. Next I'd be in the 6s for 2. And then technically, that would leave me at barium, element number 56. Well, 57 is down in the 4f. They just pulled it out because otherwise the periodic table gets a little long and crazy. Then I'd go 4f for 14. That would get me across to number 70. And then I'd be back up for number 71. I'd be back in the D block for the 5D with 10, 6P6, 7S2. That leaves me at number 88, radium. Then I'd go down and pick up number 89 through 102, nobelium. That would be the 5F for 14. 103, lawrencium is back up in the 6D for 10. And then I'd be in the 7P for 6. Today we know of 118 elements ending with number 118, oganesson. Maybe someday there'll be more. And I can only predict that element number 119, where do you think it'll go? Are you thinking like maybe someday in your lifetime there would be a 8s orbital? We don't know of any electrons today in the 8th energy level, but maybe someday. It'd be so amazing, wouldn't it? Okay, so now if I go backwards, if I go back into the chapter, number 29, question 29 looks at patterns. The periodic table is just loaded with patterns, this cross-cutting concept. What element has an electron configuration of this? And which block is it in? Use your periodic table. Okay, so a couple options. If you want to identify an element, option number 1 is to look at the very last orbital, 4s2. So I want to know what element ends 4s2. So I go to my periodic table and I just find that block and that orbital. So I'm in the S block. So I'm looking at the first 2 columns. 4s would be the 4th one down. So I'm in here. Potassium should end 4s1. Calcium! For the win, calcium should end 4s2. It should be calcium. And calcium then, whoopsies. If they ask like what block it's in, maybe we could just say like the 4s block or the S block. I should put that in correctly. Calcium. Maybe I'll just say it's like in the 4s block using my periodic table. Now the other option, here's the other option. When you see an electron configuration, I see this 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. When you see the configuration, the superscripted numbers, those tell you how many electrons are in each orbital. So you know what you could also do? You could just add up all those superscripts, and that'll tell you how many total electrons. And that would be another way of identifying the element. So like if I wanted to add the total number of electrons, I've got 2, 4, 10, 12, 18, and what do you know? 20 total electrons. Element 20 would be calcium.